Math 2414, Calculus with Parametric Curves, Video 1, Calculating dy dx. Now, normally when we have a curve defined parametrically, we have x as a function of a third variable, often t, and y as a function of a third variable, often t. But we can still view the relationship as y as a function of x, or at least on some interval for the parameter for which the graph passes the horizontal, the vertical line test. But that aside, it raises the question, how do we do the things that we've done in calculus so far, which center mainly around derivatives and integrals? Well, for the derivative, we're just looking for dy dx, even if our curve is not explicitly defined in terms of y as a function of x. So for example, let's say we want to find the slope in the equation of the tangent line to the graph of the following parametric curve when t is equal to 2. Left out the word line. And let's stretch this out just a little. There we go. All right. So our parametric curve is defined in this example by x equals t squared and y equals t cubed minus 3t. I'm going to spare you the details of sketching the graph right now and just tell you that it looks a little something like this. Starts high, loops down, comes up. Does this number, crosses itself, and I believe the orientation is like that. We'll use Desmos here in a little bit to make sure all of this is pretty good. But at some point on this parametric curve, t is equal to 2. And since we're looking for the equation of the tangent line, we're going to use point slope form, which means we need a point. So we might as well go ahead and figure out what this point is. The point on the curve is going to be the x and y we get when we let x equal 2. So we get x equals 2 squared and y equals 2 cubed minus 3 times 2. Both are fairly simple to work out. We get x is 4 and y is 8 minus 6, which is 2. So over here somewhere we have a point 4, 2. How do I know it's to the right of this? You'll have to trust me for now. But we could talk about how to find that x-intercept. Actually, it wouldn't be that hard. When you know the x-intercept, your y is equal to 0. So you would simply have to put this equal to 0 and solve it. And we would get t equals 0 or t equals the square root of 3, maybe? Yeah. Plus or minus the square root of 3? Yeah. And so that would correspond to some of these points. But anyway, I digress. So we're looking for the equation of this tangent line, which means we need the slope of that line, which means we need the derivative, and specifically dy dx when t is equal to 2. And what does that equal? Well, until we figure out how to take the derivative, it's not equal to anything yet. Well, it is equal to something, we just don't know it yet. So let's figure out how to find this derivative. The trick to finding or discovering the formula for the slope of the tangent line when your curve is defined parametrically is to use the chain rule. The version of the chain rule that says dy dx is equal to dy dt times dt dx. Is this really what I want? This is not what I want. Every time I do this, I always write it wrong at the beginning. We're assuming y is a function of x. So let's start with dy dt. Then that would be dy dx because we're thinking of y as a function of x times dx dt because we also have x as a function of t. So it's the differential form of the chain rule. Usually it's times the derivative of the inside, but this is essentially the same thing. And if you notice, parked right in the middle, we have a dy dx. So we can solve for that by simply dividing both sides by dx dt. Therefore, dy dx is equal to dy dt over dx dt. And although the dt's don't technically cancel, if you thought about this as one fraction over another, the dt's would cancel, leaving you dy over dx. So just looks like the correct setup, and it is. So this is the formula that you need to know for calculating the slope of the tangent line when your equation is defined parametrically. dy dt equals dy dx equals dy dt over dx dt. Let's figure out what that is for our current curve, which has x equals t squared, y equals t cubed minus 3t. Then dy dx, which is still measuring slope, change in rise over the change in run, instantaneously if I must. But dy dx is going to be dy dt over dx dt, both of which are very easy to calculate. The derivative of the y equation, this one right here, is 3t squared minus 3, and the derivative of the x equation is just 2t. Of course, this raises the question, what happens when t equals 0? We'll discuss that in the next video. But now that we have our slope of the tangent line in terms of t, we can just plug in the t value that we have when we have the slope of our tangent line. So the slope at t equals 2 is dy dx is equal to 3 times 2 squared minus 3 over 2 times 2. Let's see, the top is 12 minus 3 is 9. Is that right? 9. And the bottom is 4. So about 2.25. Well, it's exactly 2.25, but 9/4 is the slope of the tangent line at t equals 2. But that's not all we were asked for. We were asked for both the slope and the equation of the tangent line. But remember, to make the equation of a line, it's really handy to have a point and a slope. We already have the point. It was 4, 2. We just found the slope. It was 9/4. And so the equation of the tangent line, is, I'll remind you of point slope form, y minus y1 equals m times x minus x1. But that's kind of college algebra-ish. By now, you should just know how to set it up. The equation of the tangent line is y minus the y-coordinate, and the y-coordinate of the point was 4, I believe. No, it was 2. Equals the slope, which was 9/4, times x minus the x-coordinate, that was 4. And if we wanted it in slope-intercept form, we could just distribute to get y minus 2 equals 9/4 x minus 9, because the 4's cancel, and then add 2 to both sides. Y equals 9/4 x minus 7. I'd like to confirm that this is actually the tangent line, so we're going to jump over to Desmos real quick. I've already got the parametric curve set up for x equals t squared and y equals t cubed minus 3t. If you're wondering how to do that, go to the previous series of videos. Watch the video about graphing parametric curves in Desmos. And I've already got it set up to put 2 into my 2 functions to give me an ordered pair. So there's our point at 4, 2, like we thought it was. But I want to graph the equation of the tangent line and see if it really is. And that tangent line was y equals 9/4 x minus 7. And let's make it a different color just so it's not blurring together. And let's make it dotted. And then let's zoom in to the point of tangency just to make sure it's doing what we think it should be doing. And yeah, it looks very tangent. In fact, it looks like it coincides with it, but I'm sure if we zoomed in enough, we would see the gap between the line and, well, maybe not. It's almost like the second derivative is constant. Okay, well, we've lost resolution, so let's just go back. But, I mean, it clearly looks like the tangent line. So finding the slope of a tangent line and more generically finding the derivative is actually pretty straightforward when you have a curve defined parametrically. Just remember that dy dx is equal to dy dt over dx dt.